Hello and welcome you all for today's class on part 3 of solution, chapter 2 of class 12. In the previous video, we looked into the Henry's law, Raoult's law and numericals based on these laws, and also ideal solution and non-ideal solutions. Now, in this part, we try to know about qualitative properties. What are these qualitative properties? And these are well-known properties of solution and what way it is useful for us. And that is the one of the topic that we are going to know about it. Secondly, what are the different qualitative properties? There are 4 qualitative properties for the study. One is relative lowering of vapor pressure. We have some knowledge about the vapor pressure, and let us know what is relative lowering of vapor pressure and is it a qualitative property. Then elevation in boiling point. When a water is added by a non-volatile solute, the boiling point of that water increases when it forms a solution. Right? So, boiling point of a solution formed by adding a non-volatile solute is more than boiling point of the water itself, the solvent itself. This elevation is called elevation in boiling point, and this is a qualitative property. And then depression in freezing point is another qualitative property. When the solution is freezed to form a solid, then the actual temperature at which it freezes is freezing point of the solution. Freezing point of the solution is less than freezing point of water if the solution is made by water. Then the difference is depression in freezing point. So it is a qualitative property, right? And osmotic pressure. We have some idea about osmosis, and let us know more about the osmosis and osmotic pressure and how osmotic pressure is a qualitative property, and the numericals based on these we are going to see that. Now, qualitative properties depend entirely upon the nature, depend upon the number of particles, but doesn't depend upon the nature of it. Suppose you have solute like urea and sugar. You know that these two substances differ in their properties. But when it is dissolved, when it is 1 mole of this solute is dissolved to form a solution, 1m solution say, then properties shown by both the solutions are same. That kind of properties are qualitative properties. That means it doesn't depend upon nature of the particle, but it depends upon number of particles only. So number of particles of solute is the matter for us. So this is qualitative property. Now relative lowering of vapor pressure. What is this relative lowering of vapor pressure? We know that the vapor pressure of a solvent in a solution, is less than that of the pure solvent. Right? So pure solvent, take an example and try to remember this. Solvent is taken as water and you have dissolved a few quantity of salt in it, non-volatile solute in it. Then vapor pressure of the water decreases, or you can say vapor pressure of the solution is less than vapor pressure of the pure solvent, that is water. Right? So according to Raoult's law, we are doing it according to Raoult's law. Lowering of vapor pressure depends only on the concentration because it is on the mole fraction. It is depending upon the mole fraction of that particular component or solvent, mole fraction of the solvent in it. Pa is equal to, or P of water is equal to P0 of water into mole fraction of water. So this is the Raoult's law expression. So it depends upon the concentration, that is mole fraction of the solvent. Now, what is this relative lowering? Let us try to know about the relationship between the vapor pressure of the solution, with respect to vapor pressure of the pure solvent. Now, lowering of vapor pressure is given by P0 minus P1. Suppose the component is 1. 1 always constitutes solvent. P01 minus P1. If it is water is the solvent, then P0 water minus P water. P water means this is the vapor pressure in solution. It is always less than vapor pressure of the solvent. So this is the expression for lowering of vapor pressure. Now what is relative lowering? Relative lowering is given by P01 minus P1 divided by P0 with respect to the original or with respect to the lowering of vapor pressure with respect to vapor pressure of the pure solvent. This ratio is called relative lowering of vapor pressure. Let us try to derive the expression, derive the relationship. Now what we get is relative lowering of vapor pressure is nothing but mole fraction of solute. How? Suppose if P0 1 minus P1 divided by P0 is there, that is directly proportional to or equal to, that is equal to mole fraction of the solute. Mole fraction of solute is given by number of moles of solute, that is N2 divided by N1 plus N2. Okay, and this expression that we can able to get. Let me tell you about something more about this also. Now we had P01 minus P1 divided by P01, right? So it was lowering of vapor pressure, P01 minus P1. This is lowering of vapor pressure. This is relative lowering of vapor pressure. Okay, this is from the expression. If you take it from the expression, P1 is equal to P01 and mole fraction of 1. If you go from this expression of Raoult's law, then P1 by P01 is equal to X1, right? It is X1. Now subtract these from 1. These equal quantities, if these are equal, then equal quantities have to be subtracted from 1, the remaining is also 1. So 1 minus this must be equal to 1 minus x1. Now if you take this simplify, P01 is to be multiplied P1 divided by P01. Right? Taking LCM and multiply these two and these two. So that is a simple calculation. And this is equal to 1 minus x1 is nothing but x2. So this is the expression that I am talking about. This is relative lowering of vapor pressure is equal to mole fraction of solute. X2 refers to mole fraction of solute. X2 by definition, this is N2 divided by N1 plus N2. N1 plus N2. So if N2 is very small than N1, solvent, much quantity of solvent is there, then we can reduce this expression to N2 by N1. So by using this, we can able to calculate the molar mass of this. So P01 minus P1 divided by P01. This is the relative lowering of vapor pressure. N2 is nothing but W2 by N2, given mass by molar mass. And N1 is nothing but given mass by molar mass. The denominator will go to the numerator. Therefore, it is simply W2 M1 divided by M2 W1. So, this is a qualitative property because this is directly proportional. This is equal to mole fraction of solute. Mole fraction of solute depends upon number of particles of the solute. And this is the molar mass of the solute. If the solute is unknown to us, we can derive this relative lowering experimentally, and after getting this experimentally, we can able to calculate molar mass of the unknown solute. So, qualitative properties rather being used for finding out the molecular mass of unknown solute. So, this is the way, or this expression will be helpful for us for finding out the molecular mass of unknown solute. Right. Now coming to, Coming to elevation in boiling point. Elevation in boiling point. Suppose you draw the graph for vapor pressure versus temperature for a solvent and for the solution formed by that solvent. Okay, so very handy example that we get is water. This is water. So water, vapor pressure of the water increases as temperature increases. Yes? Now relatively the vapor pressure of the solution is lower at any particular time and at any temperature. And at any temperature, vapor pressure of the solvent is always higher than vapor pressure of solution. Okay. Now solution also increases with increase in temperature. But what is boiling point? By definition, when vapor pressure reaches 1 atmosphere, right? Atmospheric pressure, this particular temperature is called boiling point. Since the solvent reaches it earlier, this is its point of intersection, that is del TB0, that means boiling point of water. If it is water, solvent is water, then it is boiling point of water. But the solution reaches 1 atmosphere little later at a higher temperature, and this will be the boiling point of the solution. Now this difference is called delta TB, and that difference is nothing but elevation in boiling point. This elevation in boiling point entirely depends upon the number of particles of the solute or molality of the solution. Right? So the boiling point is a bulk phenomena. At boiling point, vapor pressure of the solvent is equal to atmospheric pressure. If it is 1 atmosphere, we call it as a standard boiling point. If it is atmospheric pressure is different, at that particular atmospheric pressure, it boils. Okay, that will be the boiling point at that atmospheric pressure. Now, elevation in boiling point, that is delta TB, this is equal to delta TB, is proportional to molality of the solution. Okay, so this is an important generalization. Okay, what is that? Elevation in boiling point is proportional to molality of the solution. Can be written like this: delta TB is directly proportional to molality, m, small m, not molarity, molality. So delta TB is equal to elevation in boiling point is equal to proportionality constant Kb, where Kb is called molar elevation point, molar boiling point or molar elevation point, or bulioscopic constant, and its value for water is 0.52 kg per mole for water. Please remember this value for the water, 0.52 kg per mole, right? So this Kb, how you can define Kb? This molar elevation constant is the elevation in boiling point when molality is equal to 1. When m is equal to 1, then Kb will become delta Tb. That means molar elevation constant is nothing but elevation in boiling point of 1 molar solution. Any solute you take, prepare 1 molar solution of it and find out at what temperature it boils, that solution, right? That difference between the boiling point of the solvent and the actual answer that you have got while doing the experiment, and after doing the experiment, that difference itself is delta Tb value, right? So here this also is being used for finding out molecular mass of unknown solute. Now, as for the definition of molality, this is number of moles of solute, W2 by M2. W2 by M2 is number of moles of solute per kg of solvent. So per kg of solvent, W1 is the solvent per kg of the solvent. If W1 is expressed in grams, then 1000 should be written here. So the same expression written in more elaboratedly, delta Tb is equal to 1000. Why 1000 has come? It is a factor which you get when W1 is expressed in grams and supposed to be in kg. And W2 by M2, given mass by molar mass, is number of moles. That is molality. So this expression is being used for finding out molar mass of unknown solute, and this can be experimentally determined. Now similarly, the pressure in freezing point. Water freezes at 0 degrees Celsius, right? 0 degrees Celsius, 273.15 Kelvin. Now suppose if a solute, a non-volatile solute like sodium chloride is added to this, water may freeze at about -1 degree or -2 degrees Celsius. 0 to -1 degree, this difference is depression in freezing point. It is called delta TF, depression in freezing point, delta TF. Car radiators will be having water for as a coolant, and in cold countries this coolant won't work because water cannot move because of the temperature in the atmosphere will be less than 0 degrees Celsius and water freezes. In order to stop that freezing, so what can be added is there will be some solution is being added, or it is made as a solution, and since it has got less than 0 degrees Celsius, it will remain as a liquid. So in car radiant this is being used. Water in car radiator, it is being used as to depress the freezing point. Now there another thing is, while clearing the roads which is covered by the snow, salt is being added. Salt is added to melt the ice by reducing freezing point. So for clearing the roads also it is being done. So it is all based on the theory that the salt is added or a solution will be having less freezing point than the solvent itself. Now coming to the graphical representation. Say this is a liquid solvent and this is the solution. Liquid solvent freezes at this point, this is the freezing point, and solution freezes at this particular, this is the freezing point of the solid. Now this particular temperature is the freezing point of solution. This difference is called as delta TF. Is called delta TF, and as usually delta TF is directly proportional to molality of the solution. Depends upon the concentration of the solution that you are adding, and delta TF is therefore is equal to Kf into molality, where Kf is known as molar depression constant or molar depression constant. It is being called like that, and this value, this Kf value can be calculated for different solvents. So it is being defined like this: Kf is equal to delta TF when molality is 1. So molar depression constant is depression in freezing point of 1 molar solution. So this is the way that we have to write the definitions if it is being asked. Right. Now this is the one which you can use for calculation of molar mass of a known solute. Delta TF is equal to 1000 Kf W2 by M2. W2 by M2 is number of moles. W1 is weight of the solvent in grams. Right. Now third property, before going to the property osmotic pressure, let us know about the term osmosis. What is osmosis? Osmosis is movement of solvent particle through semi-permeable membrane. Right? Say there is a semi-permeable membrane. Say there is a concentrated solution and a dilute solution at the other end. This dilute solution gives water molecules, so that water molecules drift here, water molecules come through this, and so that its level increases and we can see the level, and this movement is due to osmosis. So movement of solvent particles from dilute solution to concentrated solution through semi-permeable membrane is called osmosis. If semi-permeable membrane is placed between the solvent and a solution, the solvent molecules will flow through the membrane from pure solvent to the solution side. If it is pure solvent and solution also, from solvent side it moves. Therefore, so this movement is called as osmosis. Okay. Now this is the semi-permeable membrane. Yeah, this is a semi-permeable membrane. This is semi-permeable membrane, and you can see from the container, pure solvent, water is there here, pure solvent to solution it will move. or dilute solution to concentrated solution, it moves so that the volume increases, right? Because of this movement through the semi-permeable membrane, we get a pressure developed in it, a pressure developed in it, and this is called osmotic pressure. Okay. Now you can see in the various way arrangement can be made. Here is a semi-permeable membrane, solution and solvent. From solvent side, solute moves. Now suppose if you put pressure over here to stop osmosis. Osmosis is stopped. This pressure that you are going to put so that this osmosis is stopped, that pressure is called as osmotic pressure. This is called osmotic pressure. Okay. So, what is osmotic pressure? Osmotic pressure is the pressure that must be applied to stop osmosis. So, from where it is to be applied? So, it is to be applied at the solution side. Solvent side, solvent will move through the semi-permeable membrane so that the pressure is developed here, and you put equal pressure to stop that. So, pressure applied to the solution front or higher concentration front to stop osmosis is called, and this pressure is called, applied is called osmotic pressure. And we find that this osmotic pressure, this pipe, is directly proportional to concentration of the solution. More the concentration, more the pressure is being developed, and therefore more we have to put the pressure to stop that. So it is depending upon concentration and the temperature, two factor. And if you convert it to the equation, then R will be a proportionality constant. Pi is equal to CRT, right? Where C is the concentration. And C can be written as N by V, and once it is written as N by V, pi V is equal to nRT, which resembles PV is equal to nRT, ideal gas equation. Okay, so easy to remember. So pi is equal to N by V RT, concentration can be written as N by V into RT, right? Or pi V is equal to nRT, right? So you can write it in the different ways. MRT also you can able to write like that. Number of moles again can be converted into in that way. Okay. Now coming to reverse osmosis. What is this reverse osmosis? We'll try to know about what is reverse osmosis. Yeah. Yeah. Since reverse osmosis plants are available, and this is a very important desalination plant. So, reverse osmosis will be consisting of a long pipe-like thing. What is the principle behind it? So, there will be salt solution or the seawater, and this is the pure water. And accordingly, this due to osmosis, water will move from here to here. Water will move from here to here from the semi-permeable membrane. So these are the salt molecules, right? So this movement is called as, movement is due to osmosis. So the volume of that increases. Now suppose we apply pressure here. We apply pressure to the solution front. Then what is going to happen? Solvent molecules return back. So when you apply pressure, solvent molecules come back. And suppose if you do it more than the osmotic pressure, and more water is being got. This is a simple principle used in the reverse osmosis. In the reverse osmosis, desalination of water is being done. So drinking water is always a problem. And there was the quotation, or we used to say that there is sea water, plenty of water is there, but we have no drinking water. but this is a solution for it. From the river, from the sea water, we can get drinkable water, right? Now you compare some of the qualitative properties. So water, okay, this is MP, boiling point is 100, melting point is 0, osmotic pressure is 0. Glucose solution 18, that is 0.1 mole, melting point is 0.19. Boiling point is 100.05. The increase in boiling point 100 to 100.05 is due to this molality 0.1. Right? So in this way you can see as 0.1, 0.2, this increase, this also increases. Melting point is minus 0.36. It is depression is taken place. More depression takes place. 100.10. And here 2.4 to 4.8 atmosphere. Osmotic pressure also is increased. So you can compare all the three. Sodium chloride solution, 0.1 solution, 0.33, 100.08. So glucose 1.1 m, but NaCl 0.1 m. Both are 0.1 m, but these are different, little different. Why it is so? Let us know more about it in the later of this session. Okay. So this is the abnormal molecular mass. Suppose it is because the sodium chloride undergo dissociation in water. If any solute undergo association or dissociation, then there is a change in number of particles. As you know that qualitative property is due to the number of particles, and if a solute considered as one particle we have dissolved, considered as one particle as stated in the formula, but when it goes it has become more or less, then qualitative property also affects. And because of which, if we try to know about the molecular mass by using this qualitative property, we get the wrong answer, and this is called the abnormal molecular mass. When solute undergo dissociation or association, molar mass obtained from the qualitative properties does not coincide with the normal molar mass. So therefore, we want a want of factor for the correction. We want a factor to make the expression that we had in the qualitative properties, to correct that we need a want of factor. And this want of factor is given as I. I tell you in a simple way. Suppose sodium chloride we have dissolved. Consider that this is 1. 1 mole of sodium chloride contains 6.022 into 10 to the power 23 number of, or 1 Avogadro number of particles of sodium chloride. But sodium chloride in water gives sodium ion and chloride ion. Now what happened? This is also particle and this is also particle. Even ions also particle. So qualitative property is doubled because one particle has become 1 plus 1, 2 particle. So the I value is equal to 2. So it is so simple as that. If one particle becomes 2, then I value is 2. Suppose if you have got this delta TB is equal to Kb into molality. This is the expression for qualitative property. This is the expression if solute doesn't undergo association or dissociation. If it undergo association, dissociation, there is a correction factor, want of factor I to be taken. Suppose if solute doesn't undergo association or dissociation, I is considered as 1. It has got no problem at all. If I is equal to 1, the expression will remain same. Now suppose if a solute undergo dissociation, the I value, depending upon the nature of it, I value will become 2, and therefore this will be 2, delta TB will be increased, so that we can have a correction factor. Okay. Now this is the one way. Suppose there is another solute, take barium chloride. If it undergo 100% dissociation, it gives barium 2 plus ion and chloride ion, 2 chloride ions. Now you can look at this, one molecule of particle of BaCl2 has given 2 plus 1 3. Therefore, what is the value of I? So 1 has become 3, therefore I is equal to 3. So this is the correction factor. Right? And suppose there is one more thing. CH3COOH, acetic acid. So in a particular medium, it is undergoing association. Two particles you have added, but this has become as one particle due to this CH3COOH. So this oxygen and hydrogen do the hydrogen bonding. Therefore, two particles behave as one particle. Two particles behave as one particle, then I value is 1 by 2. So I value may be more than 1 if a solute undergo dissociation, or I value is less than 1 if a solute undergo association like this. So quantum factor is a correction factor to be added in the expressions of colligative property in order to do the correction. The correction arises due to association or dissociation of the solute particle. Now what is quantum factor? By definition, I is equal to number of particles after dissociation or association divided by number of particles before dissociation or association. So this is a simple way of defining number of particles. In the case of sodium chloride, number of particles after dissociation is 2. And number of particles before dissociation is 1. Therefore, quantum factor is 2. Dissociation, it is greater than 1. Right? So this is the way we can make use of quantum factor. Now, there are many other definitions that you can use for the quantum factor. I is equal to normal molar mass divided by abnormal molar mass. So from the point of view of molar mass also, we can define like this: normal molar mass. That means calculated. We know about it already. If we know for the known solute, we can able to. Known solute, normal molar mass we know. Abnormal molar mass, if suppose by experimentally you found out and got the value as abnormal, then this ratio is equal to I value. Okay. So the normal molar mass for the sodium chloride is 56.5. Right? Sodium is 23 and 35.5. This is 56.5. So abnormal molar mass will be just half of it. So half of 56, around 26. Okay, 28 also. Okay, so this division will become 2. I value is become 2. So that way, I value will come correctly if you know these statistics also. This can be defined in this way: I is equal to observed colligative property divided by calculated colligative property. Observed colligative property and calculated from the molecular mass. If you calculate from the molecular mass and then find out the colligative property, that theoretical one, this is observed one, practical one. So I value can be got in this way also. Let us see the numericals pertaining to this. And before that, there is one more slide. This, if alpha is the degree of dissociation and n is the number of particles obtained after dissociation and m is the number of particles obtained after dissociation, right? And you can able to give like this: after association, it is association. M is after association. Alpha is equal to I minus 1 divided by n minus 1. For association, alpha is equal to I minus 1 divided by 1 by m minus 1. So n and m. So this is n is after dissociation, m is after association. Okay. So these are the two formula. Without that also you can able to solve the question more comfortably by knowing the basic ideas, and I will show you about this. So check your understanding. Assuming complete dissociation of the following salts in water, find out the quantum factor of the following. So it is not a multiple choice. You have to find out quantum factor for each one. So this one already I told you. What is the answer? 2. Na plus and Cl minus. For this, 2K plus and SO4 2 minus. So the totally 3. 3 are there. Okay. And Al2SO4 2 Al3 plus and 3 SO4 2 minus, therefore 5. 2 plus 3 5. K4FeCN6. So remember that it is a coordination compound. This one which is written in the square bracket entity is not going to dissolve. Therefore 4K plus, 4 particles of K plus and 1 particle of FeCN6 4 minus charge. That is one particle. Therefore 4 plus 1, that is 5, is the number of particles. Okay, so it is important question, is being asked in the examinations also. Now assuming the complete association of the following compounds, find the Wanda factor of the following. Benzoic acid CH5COH, if it undergo dimerization, dimerization means two molecules coming together to form as a one molecule. Okay, HCHO if it undergoes trimerization. So this undergo dimerization, the value is 1 by 2, and if it is undergoing trimerization, this is 1 by 3. So this is the answer of it. Right. Now objective type questions. Some more objective type questions. Which one of the following 0.1 m aqueous solutions will have the lowest freezing point? All are 0.1 m only. 0.1 m solution. 0.1 small m molality, molar solution. Which one will be having the lowest freezing point? Lowest freezing point. Okay. Now remember, delta TF is equal to direct proportion to I into Kf into molality. Now Kf, aqueous solution, Kf is same. Since it is aqueous solution, it is water. Kf is for the water, solvent. Now M is molality, it is also 0.1 only. 0.1 for all the solutions. These two factors is common, but I value is different. So those which are having more I value must have more of the qualitative property. Okay, so lowest freezing point, lowest change delta TF. Okay, lowest freezing point will be when the difference is more, then that will be having lowest freezing point. Okay, now hint, find the Wanda factor. So I value for this one is 3 plus 2 5, and for this it is 1, this it is 2, and the fourth one it is sugar, it is also 1. It is not undergoing dissociation or association. So sugar and glucose do not undergo association or dissociation. For this is equal to 1, for this is equal to 5. Therefore the answer is one which is having I is equal to 5, that is Al2SO4. Right? Now calculate the mass of ascorbic acid, that is vitamin C, to be dissolved in 75 grams of acetic acid to lower its melting point by 1.5 degrees Celsius. This is an in-text question. Kf value is being given. Kf value is 3.9 Kelvin kg per mole. Calculate the mass of ascorbic acid to be dissolved in 75 grams of acetic acid to lower its melting point. Something about lowering of melting point, then you have to recall this delta TF. Delta TF is equal to 1000 kf W2 by M2 and W1. So this is the formula. Now we are supposed to find out to lower its melting point by 1.5 degrees. This is being given 1.5 degrees Celsius. So difference is 1.5 degrees Celsius. Difference is for Kelvin scale and this Celsius scale it is same. Therefore you can take this as a Kelvin also. Right? So the 75 grams of acetic acid, 70 grams of which is solute and which is solvent. Calculate the mass of ascorbic acid. Mass of ascorbic acid. This is to be found out. Mass. So ascorbic acid, as the formula is being given, you can able to calculate the M2. And W1 is 75 grams of acetic acid is being known. Kf value for acetic acid, this is a solvent. Kf value for acetic acid is also being given 3.9 Kelvin kg per mole. So this is known, this is known, this is known, this is known, and you are supposed to find out W2. Right? So simple. Now mass of acetic acid is 75 grams. Molar mass of acetic acid can be calculated C6H8O6. By this way, you are going to get 176 gram per mole, right? Lowering of melting point delta TF is 1.5. Now applying this particular formula, delta TF or W2 is equal to, we want W2, making this as an expression. So these two are to be multiplied here, delta TF into M2 and W1, Kf by 1000. So these are the values, 1.5, delta TF is 1.5, 176 M2 and 75 W1, Kf 3.9, and we get the answer as 5.08 approximately. Hence, 5.08 grams of ascorbic acid is needed to be dissolved. This is the answer. So, your analysis should start from what is being asked. From that lower end of melting point, you should write the expressions properly and analyze what is being given and what's supposed to be found out. Right. Now coming to this. Okay. Calculate the osmotic pressure in pascals. Osmotic pressure in pascals exerted by the solution prepared by dissolving 1 gram of a polymer of molar mass 1,85,000. This is the molecular mass of this or molar mass of it on 450 ml of water at 370 degrees Celsius. 370 degrees Celsius. It is something about osmotic pressure. So you have to note that pi is equal to N by V RT. It is the 1. Now pi is equal to N is nothing but W2 by M2 by V RT. N number of moles is given mass by molar mass. 2 because of it is solute. Now in this case, dissolving 1 gram of polymer, W2 is known. Its molar mass 1,85,000, it is being given. Volume is 450 ml, it is being given. R value is known and T value is 37 degrees Celsius. But take precaution, take necessary conversion to be taken up. Before that, it is in ml, it is to be converted in liters. Okay, so volume should be in liters. 450 ml is 0.45 liter. And it is 37 degrees Celsius. Don't substitute directly 37 degrees Celsius. 37 degrees Celsius, 273. Okay, is to be added so that it is in Kelvin. So 7 plus 3, 10. And this is 11, 310. Okay, so this is to be taken care of. Right? So you can look at the board. Volume of the water V is 450 ml, 0.45 liter, temperature 310 Kelvin, and number of moles of polymer it is being given. Okay, number of moles of the polymer. Okay, then number of moles means it is 1 by 85,000 because molecular mass is being given like that. Now we know that osmotic pressure is equal to pi is equal to nRT divided by V. nRT divided by V. In this way also we can write. Now substituting these values, we are going to get 30.98 pascals. 30.98 pascals, right? And remember that what we have used the R value is 8.314 into 10 to the power 3 pascal. So this is the R value to be taken because you are asked to find out the osmotic pressure in pascals. Therefore, the unit R value should be 8.314 into 10 to the power 3 pascal liter per Kelvin per mole. So that is the unit of it, right? So thank you. So for the more number of numericals of this chapter, there is another video, numericals on solutions. You can watch that for understanding more of it. Thank you.